thanks. So thank you, Marissa, for introducing me, and it's a great honor to be here in front of you to present what we are doing as Base Baha'i Foundation. So for the next 30 minutes or so, I'm going to briefly, show you what we're doing. Before I begin our presentation, I would like to set the context here. So globally, around 1.6 billion people are, having substandard housing. They don't have good houses to live. They are living on streets. And if you look at the context of Philippines, we have about 6.5 million houses that needs to be constructed to house all the Filipino nationals. And now, in terms of construction, it's an open secret to everybody. Most of our construction uses concrete, steel, and it emits a lot of carbon dioxide. Right? So 38% of global carbon dioxide is emitted through building construction activities. So in this context, we want to emphasize the use of bamboo, not just here in the Philippines, but also globally. And the reason is that it's a nature-based solution. It's available where it's needed. Throughout the global south, in the equatorial tropics, where the countries are socio-economically developing, that's where bamboo is available. It's cheap, and it has excellent mechanical properties. And in fact, if you plant the bamboo poles now, you can harvest it as early as 3 years from now, and every year onwards, you can harvest bamboo poles. And this serves as a strong livelihood generating source of livelihood for the people, and it also provides strong material for construction. Now, I'd like to talk a little bit about our core technology in Base Baha'i Foundation, and this is called as cement bamboo frame technology. It was primarily or originally developed in Colombia. It's called as Baharete, and we brought it over to Philippines, made some changes, and then we call it as cement bamboo frame technology. Though I emphasize now, over the years the technology has advanced so much that it's unfair to call it Colombian technology anymore. We should call it Filipino technology. Homegrown, home developed, and actively innovated here in the Philippines through our partners, right? And if you look at the advantages of the houses, you can see that our houses are typhoon resistant, earthquake resistant, fire resistant, insect resistant, everything that you would expect for a conventional house. And I know it sounds too good to be true, but it is, right? So here's an example of how we build the houses. I cannot run this slide here. Sorry. Yeah. Thank you. So, our construction process for the foundation is conventional. We use conventional materials, conventional engineering. It's very easy. Everybody knows how to build it. So, reinforced concrete footing in the base. We backfill with concrete. We cast concrete, and then we build the foundation wall. It can be any material. Then we backfill. Then we cast the plinth beam. And you can see how it's so easy, it's so natural, it's so conventional. And then we cast the plinth slab. Again, very conventional way to do it. And you can see from the foundation that all the rebars are coming up, right? So this serves as a base for all the cement bamboo frame panels to be inserted. And it takes about maybe 2 or 3 hours to do all of this installation. And then immediately after we do it, we proceed to construct the the roof. And if you think about this, the entire construction process with the walls and the roofing takes about 1 week. 1 week, and we're basically done. So in this particular video, you can see that we are applying the matrix towards the end, but now we are prefabricating the wall panels with also the matrix. So once this is done, we take about 2 weeks to do the final mortar cladding, and then we provide the paintworks, and then we install the doors and windows, and you have a completed building. So this is how we build all of our affordable houses in the Philippines, and not just in the Philippines, around the Southeast Asia. So, as you know, our houses are very good in resisting typhoons. Actually, we did a full-scale test back in 2014, when we were still new to the Philippines, and we built 3 pilot houses and in the southern area of Luzon. So you can see three different houses. We tried out three different architectural styles, and then we had a weather station here that could measure the wind. And luckily or unluckily, we had a major typhoon pass exactly through the place where we had these houses. And we went back after the typhoon. You can see very minimal damages to the houses. The weather station that was here disappeared forever. We could not find it. But the last reading from the weather station was 220 kilometers per hour, right? And the good thing here is these houses are still standing. People are living there. You can go take a look, take a visit, and see how the houses have lived through the years. And if you look at the farther end at the corner, on the right-hand side, you can see we tried, building a house using the traditional approach, and you can see that the house didn't make it through the typhoon. So what I'd like to emphasize here is, it's not related to bamboo, whether or not the house is going to stand. It's actually the technology. With right technology, you can build long-lasting, permanent bamboo houses anywhere in the world. Right? So, taking this as an example, we've tried and experimented and actually built different houses. For example, one-story single detached, one-story duplex. We've also built two-story houses. And I'm really happy to say that our Filipino technology, cement bamboo frame technology, is being well known throughout the world. And we've started seeing requests from countries around the Philippines. For example, we've had collaborations with Sri Lanka, Nepal, and India, where we built CBFT houses. And what's important here is it's Filipino engineers who go there, transfer the technology, transfer the learnings we had over in the Philippines, and that they help the local nationals over there to build these houses. Right? That's something really proud to be in. Beyond this, we also have, for example, working on various non-residential projects, for example, school building, community centers, weaving centers, offices, orphanages, and also community centers. Now, to facilitate construction of all these houses, structures around the Philippines, we have a strong network of partners who treat and provide high-quality construction-grade treated poles. And in particular, we have 8 treatment facilities, 9 coming, scattered throughout the Philippines, 2 in the Luzon, 2 in the Visaya, and 4 in the Mindanao. And altogether, they can produce 16,000 poles per month. That's enough to build 150 houses every month. And at the same time, we are partnering with treatment centers in Nepal, in Sri Lanka, to ensure they can also provide high-quality treated poles in the countries. So up to now, right? So the global impact of our efforts so far is that we built around 2,000 houses. We've saved around 35,000 tons of carbon dioxide. We have sheltered over 10,000 people, and we've trained over 2,000 individuals. So now I'm going to change the topic a little bit and explain what we are doing actively at the Base Innovation Center, which is a laboratory in Manila that is responsible for research and development, including the technology, including the codes and providing inputs to codes and standards. And I'm going to show you what we're doing here to improve our technology. So I'm really happy to say that we're not alone in this, and we're actively supported by a strong network of universities in the Philippines. Actually, these are the top universities here in Manila, and together they provide an army of undergraduate, masters, even PhD students who come and work in our lab and do all the research. They are really amazing people, and they are all in this room, so you can always feel free to talk with them later on, right? And at the same time, so at the same time, we also have a strong network of international partners. For example, Coventry University in the UK, TH Zurich in Switzerland, Virginia Tech, Hong Kong universities, and also we have universities in Global South, for example, University in Colombia, Technological University Mara, Nepal, and Fiji. So there are 2 things why we have such a strong network of partners internationally. For the first, in the Global North, Coventry University, TH Zurich have bamboo experts. So they provide complementary expertise, and we work together to actively improve the technology here in the Philippines. And at the same time, we are partnered with universities in Global South so that we can help transfer the learnings here and help them become regional hubs in research. At the same time, we are partnered with local institutions, for example, ERB, which is global leader in construction, and also our local treatment partners. This is the impact of BIC so far. We have trained around 294 local and international interns. We have had about 91 student pieces and 12 journal publications, 14 conference papers. Beyond that, we have actively developed to improve the Colombian building code for bamboo. We have written, in partnership with ASAP, the new Philippine bamboo design guidelines. And also, we are releasing the world's first book on structural design of bamboo with iStruct AUP. Right? And we are working with INBAR to release a bamboo construction manual as well. Now, one of the most important things about working with bamboo is that there is a strong lack of experimental data. Right? So if you ask any engineer, I want to build with bamboo, they're going to say, no, I cannot do it because I don't know any properties of bamboo. So right now, we are working really hard to close that gap, provide the necessary data so that you can design and build your own structures. So primarily, we are working on 3 different aspects: mechanical properties, that has to do with the behavior of the material itself. We are looking into the performance of connections. That's unfortunately one of the least studied topics of bamboo engineering, but at the same time, it's the most important thing of the structure. And on the larger scale, we are also looking at the performance of structural systems that makes up all of our houses. So globally, if you look at the species available, there are around 1,600 bamboo species, but only 100 or so are used for construction. And out of the 100, unfortunately, less than 20 of them are characterized. Right? And over the last couple of years, BASE and our partners have been working really hard to characterize 7 of them. 5 of those species are available in the Philippines and are already being used for construction through our partners. Now, a typical characterization process involves testing all of these 6 mechanical properties: compression parallel, shear parallel, tension parallel, perpendicular, and bending. Right? Now, ISO standard tells that we have to test at least 30 different tests, test at least 30 samples. But very early on, we realized that 30 is nowhere enough. The natural variability of bamboo is so high that 30 is not enough. We have to test at least 100 specimens for mechanical properties. So if you want to get a complete characterization of the species, you have to test over 800 specimens. That's a lot of samples to be tested. And here's an example of how we do our tests. So you can see how we do bending in our laboratory, and it's actually, you can see in the background, R&D engineer and a student from Coventry who's helping us out. So once we do like over 150 specimens testing, we make a probability density like something like this that you see here. It forms a normal distribution. And the bending strength for this particular Hawaiian tunic has a range of 40 to about 140 megapascals, right? And average value is around 88 megapascals. But if you think about this, if you design houses using average values, then 50% of the time, your members is not going to be strong enough and the house is going to collapse. So we have to choose a smaller value that will ensure that the structure will remain standing. So the standard here is to take the 5th percentile of the sample, and we use the 5th percentile of the sample to determine the characteristic of the population. So the value that we're going to use for actual design is 55.18. So it's going to be at the lower bound of what the species will have. Now, when we do the structural design calculations, we have to, again, adopt safety factors. And the actual value that ends up for the design is around 15 to 20. So if you look at the data, you will not find a single bamboo pole that falls over there. So it's really, really safe. It has a very high margin of safety, and it's very unlikely to save any damage to the structures. So this is a data for Hawaiian tunic, Bamboost sublumiana, with complete characterization. So you can see all the properties that we need for design, and you can use this to do your structural analysis, and it's in the Philippine bamboo guideline. Now you have to realize that we did around 800, and for this species we did around 1,200 specimens, right? Now if you think about it, how many species are there in the world? Over 100 that we can characterize, we can build houses out of. And if you want to fully characterize all of them, you're going to have to do around 80,000 or over 100,000 tests. That is simply impossible, insane number. So we have to look for an alternate way of doing it. And actually, our students from Bamboost University has found a very nice way to get around this. So I'm going to show you an example. So this is a scatter plot of diameter versus thickness of all the 5 species we've tested in Philippines. So we have Bamboost of Lumiana, Kawayantinik, Bayo, Bamboost of vulgaris, Lunas bamboo, Dendrocalamus aspera, which is Botong, and Guado, iron bamboo, right? So you can see, if you look at the properties of diameter versus thickness, which is geometry, you can see there's a lot of scatter in the data. It's a mess, right? There's no pattern, nothing you can derive out of it. But if you look at the performance or the correlation between shear strength and thickness, you can see some pattern here, but in general it is still very diverse. It's still very varied. It's still very hard to see a clear trend, right? So what we found out here is, if you rearrange the geometry a little bit, then a clear pattern emerges among all the species we have tested. And that's very important here, yeah? So you can see some species here fall over here, some species fall over here, but some species fall over here. And what's important here is a common line, a trend line, can predict the properties of all the 5 species we have tested so far. And that's not even for the geometry. You can also do it for the strength, right? So you can see how a clear pattern emerges. Now here what you see is the median curve. You know we're not going to design the median because 50% of samples will fail. So we go for a lower bound characteristic. And if you look at the design curve, there will be no specimen that will ever fail if you use the design curve. So you can see a clear trend and pattern. Now, what's important here is we tried something more. So we tried fitting into this curve. We tried putting into this curve a new species that you cannot find in the Philippines. So this is from my data from Nepal, and you can see the species of Bamboost balcoa, and it falls exactly on the median line, right? So you're looking at the species that has never been calibrated to this curve, and yet this curve can predict the strength parameters of a new unknown species from a entirely different geography, right? So that's very powerful. So what it means is, now instead of testing 800 specimens for a species, you can maybe test 10 specimens and see where it falls in this line, and you can still use this derived curve to get the design values. So it's going to make things really easy for you guys. Beyond this, I'm going to talk a little bit about the connections. So in connections also, let's talk about our cement bamboo frame technology. Even a single story house like this will have maybe 20 different connections, right? So similarly to mechanical properties, the current state of the art for bamboo design is testing, right? So all the 5 connections that you see here have to be tested in a lab to find these design values, right? And simply thinking about this, if you move on to a large-scale structural system, for high construction, you will have a lot of connections that you don't know how to design. And if you follow this state-of-the-art method where you do a test, you find the correlation between maximum force thickness, you get the median value, you get the characteristic value, and then you convert that to a table, and then you design with this table. It's simply impossible to keep up with the design, right? So even a house like this one that I showed you will have 20 different connections, and you simply cannot do it. So we have to find a different way to design connections for bamboo, right? And I have something very interesting for you guys. So I'm going to take an example of a J-bolt connection that we tested in our lab, and this is how a typical response looks like, right? So about this point of time, you can see that the curve tapers off, and in structural engineering, we'd like to call it as yielding. And it's actually a very important parameter that serves as a basis of structural design. But if you go to structure further, you can also see other damage modifiers such as J-bolt straightening and damage to bamboo. But what's important here is we focus on dowel yielding first, and it turns out we can predict it. Which means you don't need to do testing, you don't need to do any further analysis. If you look at these equations, which is, as a structural engineer, we'd like to show everybody these equations because it kind of shows how smart we are, but not really. Yeah. So you can see that these, if you use this equation to try to break the Dow unit, you can see that there's only less than 4% difference. That's really important. This equation can help you predict the capacity of a J-pole connection like this, and you can alter the dimension, you can alter the species, you can also alter the specification of the steel. You can do a lot of these changes and still arrive at a value that you can use to predict. So no over testing for you guys, right? We can close our BIC from tomorrow. So we tried this out with a different species, with a different connection, and it turns out we can still predict it, about 6% difference. Okay? So these equations are not new, and it's actually already existing for timber. So we just tried it out for bamboo and see and to see how it goes, and it turns out it works very good. So I realized there's a video over there. You can see how the wood is deforming, and these equations can help you predict how much the wood will deform. Now, let's go back to the meat of my presentation. And that's the cement bamboo shear walls, right? So all of our houses are built using this technology, and unfortunately, the design of these systems is also experimental. In other words, to design this house, I first had to go to a lab and do this test and figure out the performance. But it has a benefit in the sense you have a straightforward way of designing things. But the drawback here is it allows a very limited amount of change. And I know from our partners that it's really frustrating. You want to change a little bit of the walls, you want to make a wall a little bit longer, a little bit larger, you want to use a different species, and it's quite frustrating for you to hear that it's not possible. And the reason is this: we have to base our design on experiments. And if you start making a lot of changes to the system, you will end up with a wall that's completely different from what we tested. And then we have to start over all over again, and then start testing. This is going to be really expensive and hard. So we've been working really hard to figure out how to get over this. We want to help you design bamboo houses to fit your unique needs, to fit your projects, right? So we found a way to do this, and I'll show you. Before I show you how we did it, I'll show you how we do a typical test. For example, we have a system in our laboratory that applies wind and seismic, that simulates wind and seismic loads onto the walls. And this is a typical response under wind and seismic. So what's important here is the black line. We call this a black backbone curve. And here also, similarly to what we saw in connections, the part of the curve where it starts tapering off, we call it yielding. And it turns out the yielding happens from nails and bolts. The nails that connect the frame elements, that is bamboo and timber, to the grabbing, that is a mortar. So if you load it further, you will see other damage modes. For example, flat bars, damage to bamboo, cracking in mortar, but these are not so important, right? If you load it even further, the wall starts disintegrating, right? You see separation of cladding from framing, but what's important here is you are not going to see collapse of the wall, right? So we tested over 50 walls so far over the last 5 years, and not a single time it has any wall collapse on us in the lab, right? So it's actually quite boring. You see, go to a lab, you're expecting walls to completely disintegrate, but it just stands there and the test is already over, right? So I go back to the yield point here. I go back to the yielding point here, and it turns out we can estimate it. We can predict the yielding of the walls. Right? So I'm happy to say that this is the first time anybody in the world has ever done it, and I'm really happy to share that it happened in the Philippines. And this is really good because now you can use it and to really improve the structure. Right? So this equation is very complicated. I know. Even I don't understand this realized by my students. But what's important here is these equations allow you to modify the panels. You want to have a panel that's slightly longer, slightly wider, slightly higher. You want to use a different species. You cannot find the specific material in your area. You want to replace it with something else. These equations will allow you to do that, right? And what's important here is we are going to roll this out into our design process. So you are going to start seeing the benefits of this innovation as early as next year. Okay, so please stay in tune and keep your interest. So I'd like to close this session by saying that what we are doing here is not enough. I really need your help. I really need you to be with us. Please come and join and work with us and close the research gaps together. Right? So this is my presentation. Thank you all.
Thank you very much, Nischal. So you see a lot of formulas, a lot of numbers. How do we put, how